floor is yours. Thank you very much.
Hello, all delegates. And on the audiences, I am Atikon Bongsak, an Associate Dean for Industrial Relations, a representative from Faculty of Engineering, King Mongkut University of Technology, Thonburi, Thailand. On behalf of the Dean, Professor Dr. Chai Jaturapitakun, first of all, I would like to thank the organizer for your invitation to give me this opportunity in sharing our experiences in engineering education, which inevitably needs to collaborate with industry and community. This is my great honor to join the ICME 2021. Today, my topic is going to talk about the collaborative expansion of engineering excellence with industry for self-sustainable technology during COVID-19 pandemic. King Mongkut University of Technology, Thonburi was founded in 1960. The university was named after His Majesty the King Rama IV, who is respected as Father of Thai Science. The university official seal is modeled after the royal seal of His Majesty the King Rama IV. For instance, we could call KMUTT. KMUTT is a science and technology-driven university. We have 4 facilitated areas. The original and oldest one is Bangmot campus, which is the main campus for teaching, learning, and research. Focusing on the teaching and learning, Lacheburi campus is newly expanded to develop 21st century skills in our students using residential college system adopted from Cambridge University in UK. The Bang Khun Tien campus is mixed between teaching and learning, which is the place of industrial park. So in the Bang Khun Tien campus is filled with industrial testing laboratory, pilot plant, biopharmaceutical plant, and so on, that use the university strength to serve the industry. However, one of the gaps for the university is the place of location, which impact to how easy the people get access to you. Of course, if you are really good at some research field, they will therefore get to you. But KMUTT takes this gap seriously. So the university invests in a new building that is located in a business area, so-called KX building. The KX is played in a very important role of university industry linkage. The building is utilized for knowledge exchange as its name. People from industry, SME, company, and research visitor can easily commute to the building by BTS SkyTrain. The building is filled with startup working, knowledge sharing, fabrication lab, and makerspace. That is the extraordinary step for our student, alumni, and researchers. The university has 3 faculties as established, and now we have expanded for another 8 schools. Total number of students is about 15,000 yearly with 2,450 staff. Okay, then let me jump into the Faculty of Engineering. The Faculty of Engineering, we have our own vision. Using the engineering excellence to enhance society capabilities. This is our strong commitment to serve the nation. Within the faculty, we run the administrative office of the dean together with these three strategic centers to drive our mission. The Center of Active Learning in Engineering Education is taking care of the new teaching scheme. The Center of Promoting Research and Academic Outreach, this is the center to facilitate all of our academic staff and researchers to reach out to get funding from outside of the university. And we are seriously focusing on the international activity in our faculty. That's why we have one special center, so-called ICE, International Center for Engineering, to take care of those all international activity. We have totally 229 staff, including 9 professors, 70 associate professors, 84 assistant professors, and 70 lecturers. The number of 163 researchers is also a very important workforce in our faculty. The Faculty of Engineering has 11 departments plus 1 special program. We have 23 bachelor degree, 18 master degree, and 10 doctoral degree. And this is the total number of our student in fiscal year 2020. So we have more than 5,000 students. Most of them, they are bachelor students, which is 5,460 students and 255 master students and 36 doctoral students. The most related resource to empowering academic to work with industry is strong collaboration. We have our own faculty level MOU directly to 45 companies. This is the work that I myself take care of dealing with those all companies. We are planning to increase the number of MOUs by 10% every year. As you can see, some of our partner logo display on the screen, such as PTT, Ford Motor, Thai Airways, Delta Electronics, Daikin, Denso, Isuzu, and Toyota Motor. And today my talk, I'm going to focus some story with the Saicho Denki company. For our nation, the government has specified 10 strategic trends of science and technology to be our nation issues. So I believe we are sharing some interest between the country. For example, the next generation automotive, smart electronics, and aviation and logistics, robotics. And today, my talk is related to this strategy. It's a medical hub. So we've been going well with the work before the COVID-19 explode. Since March of 2020, last year, we all humankind are facing very hard time in our history again. Inside the country, we are seeking for help in everything to fight with COVID-19, such as vaccine, antivirus medicine, respirator, healthcare unit, ICU, and so on. But look, who can better help us? Overseas business, global brand company, billionaire company. Even they can help you a bit for CSR, but not a sustainable solution. I myself also working in air conditioning and refrigeration area. So today I would like to share you some success story as our lesson learned. So what COVID-19 pandemic has escalated. This situation brings engineering and medical people to work in cross-disciplinary, work to close together as ever. The engineering support from academic sector, especially not from private sector, because they need to survive the situation. So the academic sector need to readily support to the nation. And we have learned that the quick win solution for the local problem is very important. So you need to try something new, and you have to learn, as people say, fail fast, fail early. So now it's time for innovation and prototyping. What the new thing you think? You need to immediately make the prototype and test it. And in this situation, the strong local manufacturer is a key factor of this success story. So as I said, you can try to look for help for the overseas business in your country, but in our case, it's not really work. And unbelievable that one factor, powerful alumni support, is the important factor that maybe we don't think about it. So in this slide, I just show you some selected project. On the top left in this picture, we call the ambu bag. Because during the patient transfer, we need, especially for the severe patient, we need to use this kind of equipment to help them for their breathing. And the bottom left, the prototype of negative room had been built in the hospital. So they are looking for the negative room, especially in the ER room, that you don't know yet, even the patient get infected for the COVID-19 or not. And it's come to the right picture that showing the design, the conceptual design of the cohort wall. So in this slide, I just show you the development of conceptual design of cohort wall, that is KMTT, working with the site Jordan closely. So we designed the conceptual of the urgent cohort wall that we did the review of the standard design, CDC, WHO, and NIH. We also have the healthcare unit design standard in our nation. So the cohort wall should be negative pressure, and the airflow should be arranged in the specific directional airflow. The clean air should supply in the hallway that the nurse and doctor will walk along this path, and the patient lying on the bed, and at the head direction, we will have the exhaust system to suction the air, the dirty air out of the room. And the mass flow and volume balance of the supply air and the exhaust air should be verified. For the HVAC system designed for the airborne infected control, in many rooms for the healthcare unit, previously, they normally design for the pressure, the positive pressure to protect the patient or the people inside the room from the dirtiness outside of the room. So the positive pressure room is this. Simply explain that likely you stay inside the bubble, so the positive pressure will protect you from the dirtiness outside. But for the airborne infected people, you need to keep them in the negative pressure room, because if they're airborne or their breath that contain virus, for example, COVID-19, the air inside the room should be treated before let out to the ambient, to the atmosphere. So the negative pressure will be the room playing like a sink. So all the leakage will be go inside the room. So our design with Cytodinki has been actually developed to renovate the urgent of the hospital. So this is about the display of how we actually build the, or how we actually renovate the room in the hospital, or we call AIIR, the airborne infection isolation room. So it should be fresh air 100%. It means that no recirculation air. The new supply air will always put into the room, and the exhaust air should be treated before let out to the ambient. We treat with the HEPA filter. So the air change is one important key that to dilute the concentration of the contaminant in the room. The directional airflow should be designed case by case. Actually, in our study, we need to survey the on-site first before we design the directional airflow. And the temperature control should be within 20 to 25 degrees Celsius, and the humidity control, as shown in this diagram. It will be good for the condition that protect the growth of this kind of factor, bacteria, fungi, virus, for example. So they recommend that the humidity should be controlled within 40 to 60% relative humidity. And of course, the pressure of the room should be negative, less than 2.5 Pascal. And this is the actual photo after renovation. We renovate the old ward in the hospital. For this photo, it is in the Pramongkut Hospital in the middle of Bangkok in Thailand. So you can see the exhaust system, exhaust ducting system, and the black one is supply system, because this is the cool air supply. So we then work with the urgent, with the companies, and KMTT support for the CFD computational fluid dynamic design to help the company to design the new ICU. Also, we took some parameter from the breathing cycle of human to design how much, how high, and how large of the exhaust plenum that is efficient to remove the airborne infection. And the ICU, again, has been designed for much higher air change rate, directional airflow, and again, the temperature and humidity control. The negative pressure should be much more than the AIR room. And this one is the ICU after renovation, because the ICU normally will not equip with this exhaust plenum as this big, right? So we renovate this urgently with the hospital in case of the ICU need to be used for the COVID-19 patient. And next step, we move to design and to help the hospital to renovate the OR room, the operation room. And as I explained before, the operation room normally should be designed as a positive pressure. But in case of the OR room to use for COVID-19 patient, the negative pressure room should be applied to protect the doctor and nurse who are working in the room, and also to protect the airborne infection from inside the room, not to let go outside. So we also use the CFD technique to help the company to design the dental room, because the dental room, they will normally generate a lot of aerosol. So in this case, we use the CFD to design the new directional airflow from clean to dirty. So this is again the exhaust ducting, and this is the dental bed. For this figure, is represent the dentist. So the negative pressure dental room, we need to apply much more the air change rate than the other room, because normally the dental room, it will be very small room. So we need very high exchange rate or air change rate. Directional airflow, again, need to be designed specifically and using the modern technique of CFD. And the negative pressure should be controlled less than 5 Pascal. This one is the last test development this year, that the number of infected people in Thailand increasing. So we need the modular ICU to be urgently built. So in this case, we collaborate with the SCG company. They are a very big company to fabricate the construction material and the building material. So they can design and construct the modular ICU for 10 beds within 7 to 10 days. And inside the HVAC system, air conditioning system, exhaust system, they use as same as we develop for the healthcare unit, for example, ICU. So inside the picture, this is the real picture that we took several weeks ago, that inside the room is newly equipped, that the ICU will, if you can see here, the small exhaust channel that will be in on the head direction of every bed, and outside of the system is the newly product design for the negative pressure room. So this is as much of our progress from June 2020 to 2021. We expand of more than 2,000 hospital beds in a year, 9 hospitals renovated AIR ICU across the country, fully renovated 3 OR rooms from the conventional OR room to the specific applicable for COVID-19 patient. More than 100 renovation to negative dental room. More 8 hospital ongoing project, and we have already done 5 seminars in cross-disciplinary between HVAC engineering, design, and real-case operation of healthcare unit that will be presented by the medical doctor. So that is so far our story I want to share. Be strong, be courage, be safe, and thank you for your attention. Hello, can you hear me? So, okay.
So now I would like to open to the participant to ask any question to our keynote speaker. So please.
Hi, good morning, Professor Atikon.
Yes, good morning.
Yeah, I'm Sri Yulis from the Faculty of Mechanical and Engineering from UTHM. So I have one question. Okay, question on the technology advancements in the healthcare industry in Thailand. All right. So my question is, okay, how you are going to design this HVAC engineering design to cater on the increasing numbers of the COVID-19 patients admission to the hospital nowadays? Thank you.
Yes, thank you very much for your question. Actually, this is kind of a success story I just want to share because, you know, we are working in the university, right? We have our own knowledge already. We have the technology readiness that we, I believe, we normally work very similar between like Thailand and Malaysia. We develop our knowledge, we publish our research paper, but before the COVID-19, we normally work a little bit separate from the private sector, right? So this time in Thailand, especially, I just want to share that we have many overseas company, overseas business, and they are very well known. But when the overseas transportation and logistics is already closed because of they protect the like overseas risk from other country, then all the equipment, all like the HVAC system, the old designer, they cannot get any help from the overseas mother company. That's why we should develop, or we should urgently jump into the private company that they have strong background in engineering, or they have the strong business enough to develop the HVAC system, especially for the hospital. That's why I show you the picture, and I show you the project. It is just newly happened project between KMDTT work with Saijo Denki.
Okay, thank you very much.
All right, thank you. Any other question from the floor?
Maybe I have one question. It's a general question.
Yes.
Okay, please.
Keynote speakers. This just a general question. During for this pandemic, as we know, there is many students cannot enter for this university or lab. How about in the situation of this your university? That's all.
Yes, thank you very much. I think we face very same situation because outside the university, I work with. I mean, the urgent issue is being in the hospital, right, in the healthcare unit. We need to help to protect those people, the doctor and the nurse first. But we are planning. We have the plan already that to renovate our classroom and all the meeting room to be positive or negative pressure, but it should be designed specifically. It depends on the usage of the room. I mean, if we have very good screening process, that we can screen out the risky student or risky people to not get enter into our campus, into our classroom. That the room should be positive pressure. But in case of we want to make the negative pressure classroom, we need to increase a lot of air change inside the room, but all the students should be wearing the mask. That is the idea that we are planning already.
Is it okay, Dr. Shukri?
Yeah, thank you very much for this your explanation just now.
All right. So any other question from the audience? Okay, if there is no more question, so thank you, Dr. Atikon, for your keynote speech for this morning. So I would like to pass you a digital certificate as a appreciation from the committee of ICME 21 to the keynote speaker this morning.
Thank you very much. Thank you again, organizing team, Mr. Chairman, and all the audience. And thank you very much to send me this beautiful chair. So I feel really close and really involved in your conference. Thank you very much.
All right. So I would like to convey the digital certificate for you. Okay, just a moment.
Thank you.
Okay, thank you very much. Okay, next we would like to shift to our second keynote speaker this morning. So our second keynote speaker is Dr. Osman. So he is from Sakarya University from Turkey. So he has published numerous publications such as journals and book chapters along his career. And this morning he would like to give a keynote speech with the title of Additive Manufacturing Technologies and its Future in Industrial Applications. So I would like to welcome Dr. Osman to give his keynote speech. So the floor is yours. Thank you.
Hi everybody, my name is Osman Bilgin. I am a mechanical engineer at Sakarya University. My area of expertise are CAM CAE and additive manufacturing. I mostly do research in the field of FDM and binder jetting in additive manufacturing. In this study, I will make an evaluation on additive manufacturing technologies and industrial application and share my experience. In the presentation, I will talk about basic additive manufacturing technologies and commonly used additive manufacturing technologies. After reviewing the material used in additive manufacturing, we will discuss their in the aerospace, automotive, and biomedical industries. Finally, I will offer a glimpse into the future of additive manufacturing technology. In this graphics show us commonly available additive manufacturing methods. There are several technologies in the field of additive manufacturing technologies. However, today new developments are constantly taking place and these technologies continue to develop. The main companies in the global additive manufacturing market are as follows, like Strategies, 3D Systems, Farm Group, Renishaw, X1, etc. Commonly used additive manufacturing technologies are FDM, SLS, SL, and binder jetting. In addition, electron melting technology, one of the powder bed fusion technologies, is also used in the field of defense and aerospace. You can see 3D printing, left side, middle, SLS, SLM 3D printing, methodologies and the binder jetting system showing the right side. The research materials available for additive manufacturing in the coming period are shown in the figure. We can see in the figure metals, smart materials, electronics, and essential materials. The figure on the right shows additive manufacturing applications. Figure A shows biomedical application, figure B industrial application, and figure figure C the first building produced with a 3D printer. Nowadays, it is possible to see 3D printers in almost every field. Plastic are materials commonly used in the additive manufacturing. The figure is showing an overview of high-temperature thermoplastic as a function of performance. Although the performance increases as you go to the top of the pyramid, the process difficulty and associated cost increase rapidly. The figure on the right side shows the tensile test result of high-temperature thermoplastic and their composite produced by the laser powder bed fusion method. This figure shows the market shares in different areas where the additive manufacturing method is used. This figure shows that industrial application and aerospace fields have the largest market share. The next market share is motor vehicles, products, and electronics, medical and dental products. In the Vogler report published in 2020, money spent annually in final product by additive manufacturing worldwide values are in billions of dollars. As can be seen from the figure on the right, metal additive manufacturing suppliers are predicting a market size growth of 27.9%. The figure shows metal parts used in the aerospace industry. As a result of the optimization made on the part used in the first Airbus, the weight was reduced by 32%. The second figure shows the titanium bracket connector manufactured for Airbus. This connector is 50% than the conventional design. Third figure shows the LEAP engine fuel nozzle manufactured using direct metal laser magnet. This figure shows polymer parts for use in the aerospace industry. And dedicated parts are shown on the left, and the internal bracket for the Airbus is shown on the right. Another important activity in which additive manufacturing technology is used in the aerospace industry is repair. Repairing these parts, which are very expensive, provides significant income. Figure A shows the repair moment of the damaged part. Figure B shows the damaged part, and figure C shows the treated part after the repair process is completed. With the development of additive manufacturing technologies, repair work that was not possible before has become possible. In the figure, the area and part where additive manufacturing technologies are used in the automotive sector are shown in detail. As can be seen from the figure, today many automotive parts are produced by additive manufacturing. This figure shows the market share of the automotive industry. The market share forecast planning to be formed between 2017 to 2028 are given in the chart. As the chart shows, the manufacturing market share is increasing steadily and is expected to reach $12.6 million in 2028. The figure on the left shows a large number of parts produced by additive manufacturing in order to reduce production cost. The figure on the right shows the production of different parts in the same width space. In this figure, you can see parts made of polymer produced for the automotive industry with different additive manufacturing techniques. This figure shows the adoption of additive manufacturing technology in the automotive industry today and in the next year. This process development in maintenance and repair, direct part manufacturing, gauges and fixtures, molding, prototyping, and product visualization are predicted. Biomedical field is another important sector where additive manufacturing technologies is used. In the figure, the area where additive manufacturing is used in the biomedical field are shown on the human body. In the other figure, a hip implant prosthesis product produced by additive manufacturing is shown. These implants are expensive implants used in the biomedical field. The figure shows the 3D image and 3D rapid prototyping of the aorta. The second figure shows MRT image data and 3D printing of a child's ventricular system. In the third figure, scanning electron microscope of the branched tubular structure produced with the 3D printer are shown. The figures show different implants produced in the biomedical field. In the first figure, the heart model produced by additive manufacturing. In the second figure, the implants produced for the skulls and jaw region, and in the third figure, the knee and hip implants are shown. And you can see the quality is very well and acceptable. This figure shows the market size for different additive manufacturing technologies in the United States. In the research conducted in 2017, the expected development estimates in the additive manufacturing technologies between 2016 and 2028 are shown. This figure gives an idea of other industrial application. The Eiffel Tower model produced from shape memory alloy material with 4D printer technology and the shape memory stand model produced with 4D printer are shown. In the second figure, the model produced by the traditional method, the model made of steel material and the additive manufacturing. And the optimized additive manufacturing model are seen in the last figure. significantly. The figure shows the 2018 to 2028 projections of the additive manufacturing market in the eyewear industry. It is clearly seen how fast the market share has increased. In this figure, another image related to eyewear industry has been shared. A lot of addition part we can fabricate and we can use. In the animation, the play is produced by General Electric company with a metal 3D printer. My conclusion is 3D printers are used use many types of materials such as polymer, ceramic, metals, and the composite. Additive manufacturing techniques include FDM, SLS, SLM, 3D print, DED, LOM, etc. Additive manufacturing technologies enable the production of parts with higher strength, lighter, and more complex parts produced by traditional methods in the aerospace industry. Another area where additive manufacturing technologies are widely used is biomedical application. There are many applications in biomedical area, such as hip, knee, or joint placement prothesis, artificial bone, and the tissue application. In the automotive industry, additive manufacturing technologies are used in the development of a niche product, prototyping, lightweight, optimized part, and the spare parts. Other application areas of the additive manufacturing technologies are for the printing, 3D printing of smart materials, eyewear industry, electronic hardware, energy storage, food industry, sensors, and the robotic applications. Another applications are of additive manufacturing technology is construction application. The use of the additive manufacturing technologies in the construction industry can reduce labor cost, material waste, and help produce customized complex parts that are difficult to produce with traditional methods. Thanks to low prototyping costs and unlimited design capabilities. As a result of the work done, the weight of the entire structure can be reduced by 40%. My future outlook is concept companies operating in additive manufacturing are leading the way in this field. But there are still new issues that need to be researched and developed. Reducing machine cost, shortening production time, improvement of the surface quality, increasing the measurement accuracy. Binder jetting technology is seen as an opportunity, significantly lower machine cost compared to other techniques, no size limit or limited to furnace dimension, ability to control strength values with heat treatment process, being more sustainable on an industrial scale, etc. Studies on optimization of weight with topology optimization, the use of additive manufacturing technology in almost every field. There are greater opportunities in new field of activity. Thank you for listening.
I really appreciate your effort to wake up in the early morning. I believe that in Turkey is about 4 or 5 a.m. in the morning. Okay, so I would like to pass to the audience whether you have any question to our keynote speaker.
Good morning, Professor.
Yeah, please.
I'm Kana here from UTHM Malaysia.
All right, Mr. Kana.
I have questions to ask to our keynote speaker.
All right, go ahead.
Right, my question is because I could see that the development in the rapid prototyping is very massive right now, and we could see the potential use in the engineering application. I also could see that a lot of range of materials has been progress in the era of rapid prototyping technology. And my question is, Professor, how do you see the potential use of fiber materials, for instance, carbon fiber, composite material in the rapid prototyping technology? Thank you.
Okay, thank you very much for good questions. And rapid prototyping technologies improving very fast. And the new area is composite manufacturing, carbon fiber manufacturing, like etc. And a lot of people working on about this area. Also, we are working about fabricating the carbon fiber manufacturing and composite material manufacturing. My opinion, this is very important for the industrial area. And I'm believing that improving this methodology more than faster the other area. Because, the strength and the strength weight ratio is very higher and very important the industry.
Okay, Professor. So it means to say that the equipment is already there. I mean, to develop structure that made from fiber materials.
Yeah.
All right. Thank you.
Actually, we are trying to manufacturing the machine. This is very important. We are fabricating our machine in our Sakarya University. This is very important. Otherwise, we are only user. We want to improve the technology, and we want to understand better than the technology. We want to use this machine and the technology.
Yeah, understand. Thank you. Thank you very much, Professor.
Okay, thank you, Dr. Kana. Any other question from the audience? Okay, let me ask one question to Dr. Osman. May I know what is the acceptance of from the industry in order to implement additive manufacturing, especially 3D metal additive manufacturing in order to produce an engineering components?
Yeah, actually, metal additive manufacturing is very important in the industry, but this technology, is very expensive. Machine is expensive. Also, the powder material is very expensive. I think according to the Turkey is really expensive. Approximately, machine Turkish price is 5 million Turkish liras. Approximately $500,000 at least, or euro. But industry need this technology. Some area only part quality, part strength, and the surface quality is very important. Like defense and industry or biomedical industry. And this industry using this technology. I'm believing that this the metal additive manufacturing binder jetting technology will be
important more than other technology in the industry, because in the binder jetting technology, machine cost is cheaper. Also, processes is cheaper, and this is very important. And the heat treatment process is very important in this technology. And according to heat treatment process, we can obtain different mechanical properties, our parts. Thank you. I hope enough this answer. I don't know. Thank you very much for this question.
So I'm interested regarding what you have mentioned just now. We need to improve the quality, especially on the surface quality. So meaning that metal additive manufacturing requires additional processes to improve the quality of the component. So is there any, will give any what we call additional cost in terms of the production?
Yes, exactly. The post process is very important, and the additional cost coming, but the surface quality, also dimension accuracy is very important to some field. We have to use this process.
Yeah. Okay. Any other question from the audience?
Firstly, I would like to thank for this Dr. Osman for this supported for the ICME. Thank you very much, Dr. Osman.
Thank you very much, Dr. Professor Shukri, for inviting me to this beautiful event.
Yeah, thank you very much.
Thank you.
You don't want to ask a question, Dr. Shukri?
No, because I missed in Istanbul, Sakarya.
Oh,
Okay.
all right. Okay.
Thank
So,
you.
okay. Thank you, Dr. Osman, for your keynote speech for this morning. So, I would like to pass you a digital certificate as a appreciation from the committee of ICME 21. Okay. Okay, thank you again, Dr. Osman. Assalamualaikum warahmatullahi wabarakatuh.
Thank you. Waalaikum salam warahmatullah.
Okay, bye-bye.
Bye.
Okay, I would like to invite our third keynote speaker in this morning. So our keynote speaker is Professor Yukio Miyashita. So Professor Yukio Miyashita is from Nagoya University of Technology in Japan. So currently he serves as a professor in the Nagoya University of Technology, and his research interest is more on the materials development and mechanics of materials. So this morning he would like to give a keynote speech with the title of Fatigue Characteristic of Magnesium Alloy Application for Structure of Transportation. So I give the floor to you.
So I'd like to start my presentation. So thank you very much, organizer of the conference, and especially for Professor Sukuri. So I'm very much happy to attend this conference. Unfortunately, I cannot come to Malaysia, but I'd like to introduce my research activity in this conference. So my name is Miyashita. I come from Nagaoka University of Technology, Japan. So my presentation today is I'm talking on the fatigue characteristic of magnesium alloy. And this presentation is including mainly three topics. One is fatigue characteristic of extruded material. Another one is effect of environment. And the last one is the effect of aluminum content in non-combustible magnesium alloy. And magnesium alloy has advantages for using structural material. So especially this alloy is very lightweight. And this magnesium alloy has high specific strength and high specific stiffness compared to other aluminum alloy or steel. So this is very good material for application of, especially for structure of transportation, I think. However, all material has advantage and also disadvantage. So magnesium alloy too. So one weak point of magnesium is poor workability. So because magnesium has a HCP crystal structure, so this structure, in this structure, slip plane is quite limited. And another one is corrosion resistance. So this is an example of corrosion test. So magnesium alloy are joined together with another steel or aluminum alloy. And corrosion occurred in this kind of joint. So this is a problem for structural application. And another weak point and disadvantage in magnesium alloy is low ignition point, ignition temperature. However, recently the new magnesium alloy is developed. So those kind of alloys, including calcium. So when we add the calcium like more than 1%, so we can increase the ignition point like this figure. So in the later part of this my presentation, I will introduce this kind of calcium content alloy, which is called non-combustible magnesium alloy. And this non-combustible magnesium alloy is developed now in national project. And of course, this alloy, application of this alloy is for the large structure, like a train or a car body. So in generally, if you see the magnesium product produced by a magnesium product, most of the cases that product produced by the casting, die cast. So, but in case of that, if we want to make magnesium alloy for this kind of large structure, so we need wrought materials. So in this national project, wrought magnesium alloy is developed. So I will introduce result of this research work in later part of my presentation today. So I start to talk from the fatigue characteristic of extruded magnesium alloy. So this is a very fundamental and basic property of extruded alloy. So as I said to you in introduction, most of the case magnesium product is produced by die cast. This figure shows the result of fatigue strength test and compared between the die cast one and the extruded one. So in this case, we carried out the fatigue strength test in AZ91 magnesium alloy. This alloy is including 9% of aluminum and 1% of zinc. And as you can see from this figure, die cast material shows lower fatigue strength compared to extruded one. And according to fracture surface observation of die cast material, so some cases we can recognize this kind of cast defect as a fracture origin. So when we use the extrusion material or roll material, such a kind of wrought material, so we can avoid this kind of problem, I mean that the cast defect. However, we needed to understand another specific things, characteristics in extruded material too. So this figure is showing fatigue test result. At this moment, material used was 86 one, 6% aluminum and 1% zinc are included in this alloy. So we carried out a test with a specimen in different, I mean the loading direction relation between loading direction and extrusion direction are different in the specimen tested. So L longitudinal means loading direction of fatigue test is parallel to extrusion direction, and transverse means loading direction is perpendicular to extrusion direction of the material. And as you can see from this figure, we can recognize the effect of extrusion direction on fatigue strength characteristics, as you can see from this figure. And according to the fracture surface observation, in most of case specimen in this test, we could observe inclusion as a fracture origin. In this case, aluminum and manganese are detected by the EDS analysis at the fracture origin, I mean the inclusion. And we also carried out the fatigue crack growth test with the same material. As you can see from this figure, so fatigue resistance is also depending on the extrusion direction. I mean that affected by the relation between loading direction and extrusion direction. So that means fatigue difference in fatigue strength observed in fatigue strength test like this. So it's mainly due to the difference in fatigue crack growth resistance. But when we take into account the crack closure effect, so we can get this kind of one line. So this curve of fatigue crack growth curve is arranged by effective stress intensity factor range. That means the crack closure effect is taken into account. So this difference in fatigue crack growth resistance is mainly due to the difference in crack closure behavior in different materials. So and that induce a difference in crack fatigue strength. So I move to the next topics is effect of environment. So we carried out a test in different temperature and different humidity, relative humidity condition. And the temperature changed at 20 and 50 degrees centigrade. And in this case, we couldn't recognize clearly effects of temperature. However, we could recognize a quite significant effect of humidity in this test. So if we carried out a fatigue test at high humidity condition, especially for the low applied stress and longer fatigue life region, so fatigue strength decrease like this at high humidity condition. So and we also put the P mark. So this means fatigue crack initiated from corrosion. Yes, like this. So this is an example of fracture surface observation. This specimen was broken at a high humidity condition. And as you can see from this figure, we could observe the corrosion pits at the fracture surface, especially from fracture origin. So fatigue crack started from this kind of corrosion pit. And this picture shows the surface of specimen. So you can clearly observe this kind of corrosion pit after fatigue strength test at high temperature. And this figure shows the relation between pit density and number of cycles, or pit size and number of cycles. Size and also density of pit increase with increase in number of cycles. However, when we just keep the specimen at the high humidity condition, but without cyclic loading, we couldn't observe formation of corrosion pit. So in that means both mechanical loading, cyclic loading, and corrosion environment induce the corrosion pit. So this is a fatigue, corrosion fatigue mechanism. And after pit grows to some size. So fatigue crack start to initiate from the corrosion pit like this. So first the corrosion pit initiate and the fatigue crack, those corrosion pit size of corrosion pit increase, and then crack start to initiate from this corrosion pit. And okay, I move to the last topics, effect of aluminum content in non-combustible magnesium alloy. As I explained to you in introduction, we need to develop a wrought alloy if we want to apply the magnesium alloy to large structure. So in that case, of course, we need a large seed of magnesium alloy. So, but because magnesium has a quite low formability, so if we make extrusion material with high speed, so we have like this, sometimes we have cracking problem. However, if we reduce the alloy element, so we can make extrusion material with high speed. However, so as I already mentioned it too in the introduction, so mechanical property depends on the alloy element. So if we reduce the alloy element, so basically mechanical property also decrease. So we needed to make a balance, mechanical property and work ability. I mean the extrusion ability. So another problem is I already introduced it to you. That some cases we can observe the inclusion at the fracture origin. In this paper, they observed the calcium oxide at the fracture origin as an inclusion. So I mean that if we increase the aluminum content, mechanical property basically increase, but formability decrease and also inclusion size. Some cases increase. So we need to consider effect of our element. And in this case, we carried out fatigue strength test with 3 different magnesium alloy. So when, as you can see from this figure, so comparison, if you compare the fatigue strength among 3 alloys, so if alloy has a high aluminum content, fatigue strength is high. But if aluminum content is low, fatigue strength is low. So as I already said to you, the mechanical property, also fatigue strength depends on the aluminum content. However, in case of the alloy including high aluminum content, so we can recognize this kind of inclusion, the fracture surface, but not in the alloy with low aluminum content. And in case of that, if alloy is including quite high aluminum content, so fatigue crack started to initiate from inclusion. So this figure is a kind of SN curve, but arranged by the stress intensity factor. And this dashed line is showing the threshold value. So below this line, so specimens were not broken at 10 to 7 cycles. And fatigue data, strength data were arranged by the stress intensity factor, as you can see from this figure. So that means fracture mechanics approach is quite effective to understand fatigue characteristic of this kind of alloy. And, next, we try to predict fatigue strength based on the fracture mechanics approach. So we start from this equation. So we want to calculate fatigue strength. And in this case, we need a value of delta K threshold and crack size means inclusion size. So because we assume that the crack always initiated from inclusion. And in order to predict this inclusion size, we use we predict that based on extreme value statistics proposed by Professor Murakami in Kyushu University. And also calculation of delta K threshold, we use the crack closure model. So in order to obtain this delta K threshold value, we need to obtain another parameter, as you can see from this equation. So effective threshold value is almost 0.5 according to the reference. So we can assume in this 0.5 in this calculation. And delta sigma is applied stress, so we can change it, of course. And we need to obtain this delta sigma effective stress range. So this is showing us these figures. So now here we can predict it based on the crack closure model. And we took data from the reference, for example, effect of amine content on tensile strength, we could get this kind of line. And also we can predict the size of inclusion from this figure. So this figure is showing relation between inclusion size and aluminum content. So by using this figure and this result, experimental result, data from this experimental result and equation based on the crack closure model, we could get we predicted the fatigue strength ratio. This fatigue strength ratio is the ratio between the fatigue limit. Actually, in this case, fatigue strength at 10⁷ cycle and tensile strength. So as you can see from this figure, the fatigue strength ratio decreases with increasing aluminum content until 4% of aluminum content. However, above 4% of aluminum content, so fatigue strength ratio almost become 0.4. So, and when we check the fatigue strength ratio reported in the previous papers, most of the cases they report that value was 0.4. So that means our prediction is quite reasonable. So according to this kind of calculation, we can predict the fatigue strength of the material, and also we can understand aluminum addition. So as I said to you, we needed to consider make a balance between mechanical property and the inclusion size or workability or something. So this kind of prediction is quite useful to consider those kind of things. So it's good for the could be good for the fatigue design and also alloy development. Okay, this is a summary of my presentation today. So first I explained basic and fundamental property, fatigue property of extruded material. And next one is very important in practical use, so environmental effect of fatigue characteristic of magnesium alloy. And third one is effect of aluminum content in non-combustible magnesium alloy. We propose some prediction method of fatigue strength of magnesium alloy. So I'd like to say that thank you for the many people. Firstly, our research work was supported mainly by the New Energy and Industrial Technology Development Organization, NATO. And also I'd like to thank for the Professor Muto and also Professor Zainuddin in UTHM, Malaysia. So of course, I also would like to thank for my students. They could work very hard and could get very good result. So I explained as I explained to you today. So thank you very much for your attention. I'd like to close my presentation.
Okay, thank you very much, Miyashita Sensei. So I would like to pass to the floor if you have any questions to the keynote speaker.
I have two questions for this Miyashita Sensei.
Okay, go ahead.
Aogenki desu ka, Miyashita Sensei? Konnichiwa, Miyashita Sensei.
こんにちは。
Ah. Oh,
A little bit dark.
yeah, yeah.
I'm
Just for the
Okay, please give a question to
Yes,
to
yes.
the
yeah,
speaker.
yeah. Firstly, thank you very much for this support for this ICME.
Thank you.
And then this just a general question.
Okay.
As we know, this fatigue is very relevant in the application of the engineering. Failure of this fatigue around 80% of this in the mechanical engineering. So I want to know this about this. What effect of this cast iron and the extruded? What happened of this behavior of this microstructure of this phenomenon? Because you show this extruded is more important is compared to this cast iron. Actually, what the behavior of this microstructure? And then the second one is this. I refer to your slide, Sensei, about this
Yes.
Effect of this aluminum, of the content. If the higher of the aluminum content is more reflected, more effect to the stress behavior of this
Yes.
stress behavior, stress amplitude. That means is a higher stress amplitude is a higher of this fatigue resistance. Could you explain why the phenomenon aluminum content more dominant in the fatigue strength? That's all. Thank you very much for this your presentation.
Okay, thank you very much. I'm really happy to talk with you, even through the Zoom. Not Zoom, YouTube. I don't know. But thank you very much. And first question, you mean that if we compare the cast material and extrusion material, what is the advantage in extrusion or characteristic?
Yeah.
Okay. So cast material, as you know, it's very difficult to completely avoid the problem of defect. So that is one thing. Another one is it's very difficult to control microstructure in casting process. Of course, we try, as you know, many engineers try to control the cooling rate or something, and we can control something. But actually, it will be difficult when you make a big size of a component.
Oh.
Yes, because some parts has a very thin, some parts has a quite thick. So that means really difficult to control precisely the cooling rate in each part. So, but another problem in extrusion, on the other hand, problem in extrusion is that, of course, we can avoid the problem of defect, and also we can introduce, we can make for example, small grain size through extrusion process. So that means basically strength increase by extrusion process. But however, in the same time, most of the case we have texture structure. So that means one direction strong, but the other direction weak or something. So that makes difficulty for the machine design. So, but very difficult because such a kind of texture basically induced by due to the structure, crystal structure of magnesium, HCP structure. So we must take into account those kind of effect and think we need to think the good way of fatigue design. So that is probably, is it okay for your first question?
Yeah. Enough.
Okay. Second one is aluminum content. So aluminum has many meanings. But one is that if you put magnesium, aluminum into magnesium, so intermetallic will be formed. So that intermetallic is some cases important. I mean, the intermetallic usually very hard. So that means you can improve the mechanical property by adding the aluminum content. But in the same time, those kind of intermetallic can be the fracture or fatigue origin. So just if you carried out the tensile test or something, so not sensitive or the small inclusion, but as you know well, very well, fatigue.
Yeah.
So in case of fatigue, so very, even if it's very, very small, the inclusion size, but it's very sensitive. So we must, in my presentation, I wanted to say that we need to make a balance. So we must consider the mechanical increasing of mechanical property, but same time increasing of inclusion size. So that is a effect of aluminum, importance of aluminum content in direction of the fatigue design.
Yeah, thank you very much for this,
Okay, thank you.
Miyashita Sensei. Thank you very much.
ありがとうございます。Thank
Okay,
you.
thank you,
Okay.
Dr. Shukri. So any other question from the audience? Okay.
Hello?
Okay, please. Could you please
Okay,
introduce
Prof.
yourself?
Hello, Prof. Miyashita. I'm Nizam. Okay, from the result, it showed that reducing the grain size produce better result, is it?
Sorry?
From the result, reducing the grain size is produce better result.
Better in basically mechanical property means the tensile strength or yield stress or something.
Okay, so is it possible if we can use this powder methodology method to produce this magnesium alone?
Yes, it's possible. Actually, we made it. I think when Skuri sensei was in my lab, I think one Malaysian student, she making that kind of material. But as you know, it's also same for the 3D printing as last present in keynote speech. So it's very difficult to control handling the powder, especially for magnesium. It's very active. So that is a kind of problem. But we can produce magnesium alloy with powder methodology. It's possible.
Okay, maybe thank you. Maybe last question. How about this producing this UFG through several plastic deformation method?
Sorry, can you repeat?
How about another method like several plastic deformation in producing UFG? Is it possible another method to produce this magnesium alloy?
Another production method.
Yeah, like several plastic dimension, equal channel, angular pressing.
Okay.
Something like that.
Okay. Equal channel. That techniques was many researchers has been done that techniques because we can make a very fine small grain size, and also we can improve the ductility of formability of material. That is very good way, I think. But problem is that really it's quite difficult to make a large component. So in the specimen size, it's okay. But if, as my presentation, if we want to make a car body or train or something, it's some cases difficult. So, but also some professors, they are working on, for example, FSP. It's a friction stir processing. So after making the seat by die cast or extrusion, they try to control the microstructure after the material processing. So those kind of development is quite important in future for the application of magnesium alloy.
Okay, thank you, Prof.
Thank you very much.
Miyashita.
Thank you.
Okay, thank you very much to our keynote speaker, Professor Miyashita. from Nagoya University of Technology, Japan. So I would like to pass the digital certificate to our keynote speaker. So please wait for a moment.
Oh, thank you.
Thank you very much again.
Thank you very much.
お願いいたしました。
And I'd like to say thank you for this very nice. Okay. ありがとうございます。
Okay,
Thank you.
thank you very much. So let us move to our last keynote speaker for this morning. So his name is Associate Professor Dr. Waluyo Adi Siswanto from Universitas Muhammadiyah Surakarta, Indonesia. So he obtained his PhD from Royal Melbourne Institute of Technology, Australia. So this morning, he would like to give a keynote speech on the topic of kinematics simulation learning tools, eccentric reciprocating slider mechanism based on vector approach in SMATH. So the floor is yours. Go ahead.
For inviting me to share my research entitled Kinematic Simulation Learning Tool of Eccentric Reciprocating Slider Mechanisms based on Vector Approach in SMAT. Before I continue, let me introduce myself. My name is Waluyo Adi Siswanto. I'm currently an associate professor at the Department of Mechanical Engineering, the Faculty of Engineering, Universitas Muhammadiyah Surakarta, Indonesia. I'm also the Director of Collaboration and International Affairs, Universitas Muhammadiyah Surakarta, Indonesia. Okay, now we start from the research objectives. The first one is to provide a simulation tool to visualize kinematics behavior of eccentric reciprocating slider. The developed tool is expected as a reprogrammable platform enabling users to customize and modify for design optimization for reciprocating sliders. Okay, let me start with what is the eccentric slider. This is the very basic kinematic tools that consists of crank. This is the center of the crank, and that's the length of the crank, and also the connecting rod. And if the center of these two lines not parallel or not in line, therefore this is the eccentricity. So if we put the diagram, a simplified diagram, so the crank stands from A to B. The crank is represented by the line from A to B, and the connecting rod representing from the line from B to C. And the eccentricity is represented by E here, and there are three angles, theta, delta, and phi. From the analysis of the vector kinematics, it starts from the very simple consideration, which is the general motion consists of translation and rotation. So this is the velocity diagram, and this is the equation consists of the translation and tangential rotation. And for the acceleration, also the same. For the acceleration consists of the translation, and the rotation consists of two parts. The first part is the normal rotation, and the second part is the tangential rotation. For the implementation in SMAT, The slider, the position of the slider representing by X, the velocity of the slider representing by VC, and the acceleration of the slider representing by AC are all written in terms of theta, EC, AB, and BC. So all these design parameters are written simultaneously to be the function of the position, the velocity, and the acceleration. So all kinematics variables are defined as simultaneous for design parameters. For the platform design of the simulation tools, the design consists of several working areas. Actually, there are 3 working areas, and there are 3 snippet steps. So the snippet steps here means the equations or the program that are coded in SMAP, and this coding can be hidden or open according to the requirement. If we want to show the program to our students, for example, and then we can open the snippet, and then the students can learn how to do the program, and if they want, they can do the customization and modify the programs to make it better, or to put some more parameters for their research. So once the equation already implemented, then the working area is the display that show the results of the calculation or the analysis. So the second step is the more complicated equations involved in the slider, and then shows in the working area number 2, step number 2, showing more complicated functions and variables. For example, here there are 2 functions, the velocity, the acceleration, and the velocity magnitude altogether, as well as to introduce another position consists of 4 parameters altogether in one function. And snippet number 3 is the most complex one. All kinematic variables are written in 4 design parameters altogether. Then the working area step number 3 is the most complicated, and it can be used for some other applications. Okay, now let me show you how the program or the simulation tool works. This is the information of the general slider, where the students or the users can put the input data. For example, here the velocity, the angular velocity, as well as the angular acceleration. So once the students input the data, and then this is the snippet of the equations involved to calculate or to draw the rotations of the crank, and it can be shown directly. For example, if the user put 0 here, then the result will be automatically adjusted and then showing that the angular velocity along the angle are always constant. So this is the input data, this is the coding snip. If we click this button, it will close this snippet, then the user cannot see at all. So what they see is only the input data and the results only. This snippet area can be locked by using password, for example. Then if you don't want to show the equation inside, then you cannot share the password, then the user cannot see what the equation inside. Okay, for the second step, which is more complicated, so these are now calculating the acceleration by using vector equations altogether, and then at the end, it shows the velocity of the slider in terms of the 4 parameters. So in this display, the user can use different parameters and then plot all of them into a single plot. Then they can compare the behavior of the results. For example, here, this is the comparison of the different eccentricity. If the eccentricity is different with the crank and the connecting rod similar, then the behavior that we can see is a bit different. So what it means, the user can compare different design parameters and then see the behavior in terms of the velocity. Now, we go to the applications. So the first application is the kinematic investigation of eccentric reciprocating slider mechanism. This is the investigation of the eccentricity involvement towards the velocity and acceleration. If you want to see different eccentricity and then see the result variables of the velocity and acceleration, then you can plot the graphical results whenever you put different input data in terms of the parameter. The second one is you can show the graphical kinematics behavior not only numerically but also graphically, at least one complete cycle. So you want to see the behavior of the slider, you cannot only see one single location only, but you have to see the whole cycle, at least one cycle. And the third one, in the case of the rotation of the crank, whenever it's not constant but increasing, then observing the first cycle would not provide sufficient information, because you have to see some more cycles, because the velocity or the angular velocity is increasing. Therefore, the behavior of the first cycle will be different if you see from the next cycle. And the third one, the fourth one, since the simulator considers all design variables as simultaneous functions, the simulation tool can be used to optimize design parameters to improve the performance of the slider. For example, if you have different configurations of the design parameters, and then you can see the comparison between different configurations in one single plot, then you can select which one the best performance of the slider. Of course, whenever you use this tool, then you can use this as a quick feasibility study of the working slider. When you design the slider, if you put the length of the connecting rod, the length of the crank, and the eccentricity not all values can be working in that slider. So you can see the feasible values of the configuration that result in the best performance of the slider. Okay, this is the illustration of the results of the tool that you can use simultaneous comparison of different parameters. For example, x is the variable, and the second value here, the second argument here, is the eccentricity, and the third one is the crank, the length of the crank, and the fourth one is the length of the connecting rod. So the first three configuration here showing the same length of the crank as well as the same length of the connecting rod, but different eccentricity. And the fourth simulation here, it simulates the same eccentricity with the third one, the same length of the crank with the third one, but different length of the connecting rod. Then when the program runs, then we can see the difference of these different configurations. Since this is acceleration, if you would like to have the very smooth movement of the slider, the acceleration must be put as a very minimum. Because when you have the very high acceleration, it means there's the implication with the vibration of the slider. Then, as a result, the slider will be vibrating and it will not perform smoothly. So this is the application for the investigation of the acceleration of the slider. So this application is to reduce the vibration of the sliders by comparing different configurations of the slider. Then if you change, then you can find which one the lowest acceleration of the design parameters. Another application is for the feasibility of the design parameters. If the line is discontinued, so it means, or it indicates a jam system. So the system of the slider would not move because the parameters does not make sense and it makes the slider stop. So graphically, it can be seen here whenever the line is discontinued or not connected, then this design is not a feasible design. So it means cannot be applied as a slider design because the slider will stop somewhere and then it won't run. So you can put as many as design configuration as you wish, and then you can plot in one plot, and then you can see the behavior, the characteristics of the acceleration of the slider, or you can see as well, if you want, you will see the velocity as well as the position of the slider according to the cycle. Okay, that's the application of this tool. And the conclusion, the calculating kinematics behavior using vector approach is very effective, because when we use the vector approach, then we can program the vector approach very conveniently in estimate, and then you can calculate almost every variables involved in kinematics of the slider. And the calculate variables also can be written in multiple functions depending on the design parameters. So what it means here, for example, if we have the acceleration, and this acceleration consists of several parameters at the same time. So you can see in the previous slide that the parameters altogether considered 4. Every variable consists of 4 parameters, and then you can do some configuration of the form as you wish, and then you can see the results when you run the simulation tool. Okay, thank you very much. I hope this is useful, and thank you for allowing me to share the research that what we have done so far. Thank you very much. See you next time.
Okay, thank you very much again to Dr. Waluyo for his keynote speech. So, unfortunately, Dr. Waluyo is not available this morning in our live session. So we are at the end of the keynote speaker session. So I would like to appreciate and thanks to all our keynote speaker to give their keynote speech for this morning. It is very interesting topics. At the same time, I would like to give a digital certificate to our last keynote speaker. So wait for a moment. Okay, thank you very much again to the audience who pay an attention and also your patience throughout the keynote speaker session. So I think we can finish our session now, and I pass the next session to our Master of Ceremony of the ICME 2021. Thank you very much again. See you.
Thank you very much to Professor Dr. Irwin bin Abdul Rahim for being the moderator in the second part of the keynote presenters today. Ladies and gentlemen, on behalf of the organizing committee, I would like once again to thank you for being here. We still have the parallel session after this, but before that, I would like to invite the Associate Professor Dr. Buhari Mansur, the Dean of Faculty of Mechanical and Manufacturing Engineering, University Tun Mesin on Malaysia, to deliver his closing speech for the 11th ICME 2021. And with that, I would like to welcome Associate Professor Dr. Buhari for his speech.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh, and good evening to all. Alhamdulillah, after 2 days of fully packed program with nearly 100 papers being presented together with 9 outstanding keynote speakers from all over the continent, and a forum session by the key players among the leaders from universities, industries, and also from communities. This conference has come to its end. This conference, I can say, is a big success to the faculty and also university, considering the current situation of the COVID-19 pandemic. Hence, actually, this is the first fully online conference that ever being organized in-house. And what's more, this is the first time in the conference history since we started 10 series ago, I think which we add up to the forum session that discussed the conference theme from the eyes of the expert, hence making the discussion become more lively and impactful. This is also the first time actually where we gather the most number in international keynote speakers from different countries, where we attract more international participants from this year. On behalf of the Faculty of Mechanical and Manufacturing Engineering, University Tun Nusantara, Malaysia, I would like to proudly close this ceremony of the 11th International Conference on Mechanical and Manufacturing Engineering 2021, or we can say that ICME 2021. I would like to convey a beautiful and appreciation to all keynote forums, keynote speakers, and also invited speakers, the paper presenters and participants for their willingness to share findings and ideas of the current research, development, and commercialization. I also would like to thank all sponsors in securing ICME 2021 in terms of financial with their big heartedness contribution. May this conference bring up closer together in research, development, and also commercialization that will foster friendship and cultivate future cooperation. I sincerely believe and definitely certain that ICME 2021 will be successful and benefit everyone. Finally, I would like to thank and congratulate to organizing committee for executing an outstanding job in making ICME 2021 a great success. I believe all the hard work has been paid off after completing this 2 days event, and may we continue to be in the success journey again in the future. Before I end, I would like to welcome all of you participants and also the listener, looking forward for our next series of ICME 2022 next year, inshallah. And finally, with that, I end this by reciting a salawat ala Nabi sallallahu alaihi wasallam. Allahumma salli ala Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Wassalamualaikum warahmatullahi taala wabarakatuh.
All the participants, all the experts in mechanical and manufacturing engineering in the future. Ladies and gentlemen, all right, the parallel session will begin around 11:30. But before that, I would like to invite all the participants and all the presenters, all the keynote speakers to switch on the camera on the laptop or on your handphones. We will have a photography sessions right now. So I really hope that everyone's ready and we can see that everyone is switching on the camera. Yeah, please smile. Okay, this is for the first page. One, two, three. All those handsome men and beautiful ladies on the camera, please smile. And we're gonna have the second page now. Smile. One, two, three. All right. So do we still have another page? Yes. All right. And that is all. Ladies and gentlemen, we would like to say thank you once again to all the participants and presenters. And don't forget, we're going to have our parallel session in a few minutes. And before that, I would like to thank all the sponsors for the 11th International Conference in Manufacturing, in Mechanical and Manufacturing Engineering 2021, organized by the Faculty of Mechanical and Manufacturing Engineering University Tun Sen On, Malaysia. And the sponsors are Yayasan Amal Malaysia, the headquarters, Yayasan Amal Malaysia Johor, and University College Tati, which stands for Terengganu Advanced Technical Institute. To all the sponsors, thank you very much. And with that, don't forget the parallel session after this, ladies and gentlemen. With that, I would like to thank everyone for being here in the 11th International Conference in Mechanical and Manufacturing Engineering. Thank you once again. Stay safe, everyone. And thank you very much.
All participants say bye-bye.
Climb 1000 feet right, turn runway 16, clear for takeoff, Dynamite Delta, Uniform Alpha. orbital field initially must go to equal departure F1 contact radar 124.7 runway 16 clear for takeoff 9 Mike Delta Uniform Alpha.
Saya Muhammad Amir Hakim Dewan Wahab, proses safety executive di Petronas Gas Berhad. Antara perkara yang saya dapat ketika saya join program-program yang dianjurkan oleh UTHM secara amnya dan FKM secara khasnya adalah tidak lain dan bukan adalah meningkatkan soft skill di dalam diri.
The mechanical engineering program offered in UTHM had equipped me with the necessary engineering fundamentals and became a platform for me to explore my opportunities and strengths to kickstart my career as a young engineer.